Hi, my name is Tim Brecht, and on the right, right above me, you'll see that my co-authors are pictures of them: Hoang, Ben Cassell, and Samar Al-Kiswany. Today I'm going to be talking about RocketBufs, our framework for building in-memory message-oriented middleware. Message-oriented middleware systems are often used to build applications or services that process large amounts of data. Variations of MOM systems include message queuing systems, event-based systems, and pub subsystems. In MOM systems, data in the form of messages are created or obtained at the producer and published to brokers, which can then further disseminate that data to consumers. These brokers allow the producers and consumers to operate independently, and many MOM systems enable the support for large numbers of consumers by replicating data across multiple brokers and having subscribers subscribe to different brokers. There are a large number and variety of MOM systems. Apache Kafka, RabbitMQ, and Redis are examples. In addition, Amazon Kinesis and Google Cloud PubSub are services provided by cloud providers. So there are lots of MOM systems. These are just a few examples. And despite the fact that there are so many, there are new systems that continue to be built. There were 6 new projects started in the last 5 years. And despite that, none of these, to our knowledge, systems are using the advanced data center networking technologies that are available today, like RDMA, DPDK, and TCP Direct. Now, part of the reason for that is because it's difficult to support multiple networking technologies, and partially because the APIs and abstractions provided by these technologies are very different from TCP, and they're quite hard to program. So some of the goals of RocketBufs are: we'd like to provide natural abstractions and easy-to-use APIs for building MOM systems. And importantly, we want to support different networking technologies and transport protocols. The idea is that if the application, or if the MOM application is built using RocketBufs, we should be able to add new technologies to RocketBufs, and the applications should get access and be able to use them with no changes to their code. We want to provide support for flexible MOM topologies, and we also want applications whose resulting performance is efficient and the system is scalable. So RocketBufs applications would write calls to our RocketBufs library, which uses RocketNet to translate the operations from RocketBufs into the networking layer. So our current prototype, we support TCP and RDMA, and we believe that by providing this RocketNet layer between RocketBufs and the networking layer, we should be able to fairly easily add support for other technologies. I'm now going to provide you with a bit of motivation behind some of the design choices we've made in RocketBufs and explain some of its key abstractions and components. So some of this work was stimulated by some work we had done previously in disseminating live streaming video in data centers. And in a similar fashion, we noticed that MOM systems also contained key components where they have data that needs to be transferred from memory in one host to memory in another host. And so it's also often the case that data ingested by at one host becomes output to other hosts. And so these buffers, where either video is stored or in MOM system cases, messages are stored, these buffers became the central abstraction around which applications can be built in RocketBufs. And this is where the name RocketBufs comes from. The system's designed around fast and easy transmission of data from output buffers on one host to input buffers on another host. Because the data in buffers may be used for input or output, we provide C++ classes to simplify application building. These are called ROut and RIn, ROut for producing data and RIn for ingesting data. And each of these is associated with a buffer, which is provided and supported in RocketBufs. Now, to demonstrate the usefulness of our system and to study its performance, we've built a use case. We've studied a use case. Our application that we built is a pub subsystem called RBMQ for Rocket Buffer Message Queues. In this system, topics are mapped to buffers. Publishers send messages using ROut by connecting to RIn objects on other hosts. And then the broker splices data into this output buffer, and splicing is explained in the paper. The output buffer then can be used to transfer data further to the subscribers. To evaluate RBMQ, we run a broker on a single host, a 2.4 gigahertz Intel Xeon with 10 cores, which contains 4 40 gigabit NICs, network interface cards. And publishers and subscribers all use similar hosts that contain 8-core 2.0 gigahertz Intel Xeons and a single 40 gigabit per second NIC. To further demonstrate the flexibility of RocketBufs and our resulting pub subsystem RBMQ, we evaluate RBMQ by running several different configurations. So the first configuration is it uses TCP between publishers and brokers, and TCP between the broker and subscribers. And this is denoted as RBMQ TCP TCP. And there's a version that contains flow control and a version that does not implement flow control. And in the results I'll talk about here, we're not going to include the flow control results. We'll talk about the no flow control results. You can see and find out more information about the results with flow control in the paper. Now, this is the kind of configuration that might be used if the publisher and subscriber are outside of the data center that the broker is in. In some cases, the broker and the subscribers might actually be contained in the same data center. And if that's the case, they can take advantage of RDMA to transfer data efficiently within the data center. And in this case, we call this RBMQ TCP RDMA because producers are producing data using TCP, and the data is transferred between the broker and subscribers using RDMA. And finally, we'll consider the case where all of the components live in the same data center, in which case we can use RDMA for all communication. And so that's RDMA between producer and broker, which is this RDMA, and then between the broker and subscriber, which is that RDMA. Now, in order to compare performance with existing systems, we chose to use Redis. We use it in pub sub mode because it's widely used and has been reported to have quite good performance. Its brokers, subscribers, and publishers. The broker it provides is implemented in C, and we've implemented subscribers and publishers, which are also implemented in C. We've also compared against RabbitMQ because it's widely used. It's implemented, and its brokers implemented in Erlang, and RabbitMQ, is in Erlang. And we've implemented publishers and subscribers in C for performance reasons. So the broker in this case, or our publishers, are going to publish data to the brokers, and the brokers are going to disseminate all messages to all subscribers. And we're measuring the throughput and CPU utilization, as well as latency, which is covered in the paper. So we plot in two graphs. The graph on the x-axis, the x-axis shows message sizes, And in the left graph, we're showing the throughput in messages, thousands of messages per second, so messages times 10 to the 3. And good put, which is application bytes, or the throughput in terms of raw application bytes, including no headers or system byte overhead metadata. It shows the throughput as the message size increases. So as you would expect, as the message size increases, the throughput in terms of messages per second goes down, and the good put goes up. So that's the performance of RabbitMQ. It's not very, very good, largely because it's implemented in Erlang. And when compared with Redis, implemented in C provides quite substantially better performance. When looking at RBMQ and the performance of the TCP version without flow control, we see that it compares quite favorably with Redis. Now, all of these systems are using TCP for all communication. As I've noted, if the brokers and the subscribers happen to be located within the same data center, there's an opportunity to use RDMA between the brokers and the subscribers. In this case, it's the orange line we see appearing here. And we see that by using RDMA for one component of the communication, it significantly improves throughput. So quite a big gain when compared with using all TCP. Now we'll examine the case where all communication is done using RDMA, so which is often the case, or which could be the case when all of the components are located within the same data center, which is quite often the case in large internet services. And this is the purple line we see now, which is showing much higher throughput now when compared with the other systems. Part of the reason for that is that RDMA does not require the use of the kernel or the CPU in order to move data between hosts. It's all offloaded on the NICs. And so we can see we get very high throughput, and in fact, there's the throughput, or the good put, is limited by the NICs. There's actually CPU headroom here to get higher throughput if we had faster NICs. Now, in pub/sub systems, the subscribers are actually responsible for processing the data and doing a lot of application logic. And so an important thing is to make the subscribers as efficient as we possibly can. So let's examine the CPU utilization on the subscriber end of things. So this graph shows for different message sizes, the CPU utilization lower is better. And what we can see is, and this is for processing 50,000 messages per second, so they're all sustaining the same messaging rate. We can see that Redis, the key takeaways here are Redis is quite high. That's due to extra memory copying it does before it makes the data available to the subscriber. It makes a copy of that data and then provides that buffer to the application. So it's a data copy that's implemented in Redis. RabbitMQ is slightly better, and we see that the RocketBufs version of RBMQ is significantly better because it avoids all that data copying overhead. It makes the buffer directly available to the application. And the key takeaway here is that for these various sizes, RBMQ has very negligible CPU overhead. So in summary, RocketBufs is a framework for high-performance MOM systems. It provides memory-based buffer abstractions, APIs for producing, disseminating, and subscribing to data. It supports buffer splicing and flexible MOM topologies, and supports multiple transport protocols, which require no application code changes to use, just changing a configuration file. In terms of performance, we get good performance for TCP compared to production systems, but we get substantial gains from RDMA, and provides good boost in throughput and reduced CPU utilization. And the last slide contains discussion points.